is here to tell you about it. All right, take it away, Josh.
Okay, thank you. Okay, so you can see my screen?
Yes.
Yep. Okay, good. Great. All right, well, thank you. It's a pleasure to be with you all virtually, and I want to thank the organizers for the invitation to speak to you today. I'm going to be, we had a little bit of a switch, as you know, in the schedule. So I'm going to be focusing mainly on kind of the observational aspects of dark energy and cosmology. And tomorrow you'll hear from Paolo Cremonelli, who will really focus more on the theoretical side of the subject. So ideally, maybe those would have been in reverse order, but I think it's still fine. I think the two talks hopefully will complement each other. I don't know how you are doing it with questions. I'm happy to take questions during the talk or at the end. I might not. Yeah, how do you want to do that?
What we have been doing so far is that we have a chat as well as this other Google Doc where, because this is being streamed on YouTube as well, that people can ask their questions. And then after so I'll keep an eye on the chat, and Great. After the talk, then, we'll go through the question.
Okay, yeah, and if you could, ping me, because I don't have the chat window up in front of me.
Absolutely.
Okay, all right, thank you. All right, so let's jump in. This image here is of the top of the mountain at Cerro Tololo. This is CTIO, Cerro Tololo Inter-American Observatory. This is a astronomical observatory in the Andes Mountains down in Chile. And this is the site of the Dark Energy Survey. And I'm going to be using later in the talk the Dark Energy Survey as kind of an example of one of the surveys, prominent surveys that we're using to try to get at the nature of dark energy. So I'll be using it as kind of a worked example. And the Dark Energy Survey was carried out with the telescope inside that silver dome in the center. Okay, so just a kind of basic reminder of where we are in cosmology. At the beginning of 2022, we have a very well-tested 6-parameter cosmological model that we call lambda CDM, or lambda cold dark matter. And it has several basic key elements to it. One is that the universe is expanding from a hot, dense early phase that we call the Big Bang that happened about 13.8 billion years ago. Just after the Big Bang, we have our model has an early epoch of what we call accelerated expansion, or what's conventionally called inflation, that produced a nearly flat and smooth spatial geometry for the universe, and also through quantum mechanics generated large-scale density and potentially gravitational wave perturbations. From those density perturbations, those are gravitationally unstable, so over cosmic time, those perturbations grew into forming the large-scale structure, and in fact, ultimately responsible for all the structure we see in the universe today. And that picture holds together very well with what we observe in a universe that's about 25% cold dark matter, and about 70% of the energy density is in a cosmological constant, this thing called lambda, or vacuum energy, and about 5% in ordinary baryonic matter. Moreover, we've known for the last 20 years or so that the universe is now again accelerating. And that's going to be the focus of this talk, is trying to understand what's caused this second phase of cosmic acceleration, which the universe is currently undergoing, that started maybe 5-7 billion years ago. And this simple picture is consistent with all the data we have, aside from some tensions that we'll talk about. All the data that we have from the cosmic microwave background, observations of large-scale structure, observations of weak and strong gravitational lensing, supernovae, clusters, light element abundances. etc. So it's really quite remarkable. We now have cosmology over the course of my professional life has gone from a data-starved to a data-rich science. And what's interesting to me is that over that period, still a relatively simple model has sufficed to be able to provide a framework for all of this rich data that we see. So this is just a pictorial representation of this, which is commonly shown. The Big Bang on the left, that period of very rapid accelerated expansion called inflation, really in the first fraction of a second after the Big Bang. About 380,000 years after the Big Bang is when photons decouple from the matter. That's when the cosmic microwave background gets imprinted, followed by dark ages, and then we believe first structures really start to form, luminous structures about a few hundred million years after the Big Bang, eventually growing into the rich web of large-scale structure we see. And this kind of cone that's flaring out, to the right is again that indication that the universe is now undergoing this second phase of accelerated expansion. So that, in a nutshell, is our current picture of cosmic evolution. Sorry, I think I'm missing something here. No, okay, yes. As I mentioned, again, around 380,000 years after the Big Bang is when the photons in the microwave background decoupled from the matter, since the matter went from being ionized plasma to neutral hydrogen. The photons essentially freely stream to us from that epoch. And so this is a picture of the small 1 part in 100,000 fluctuations in the temperature of the microwave background. The mean temperature is about 2.7 degrees Kelvin. So the hot spots are a part in 10 to the 100,000 hotter than the blue spots. And those hot and cold spots are a reflection of small amplitude density perturbations at that early time, which we then believe grew into the nonlinear structure that we see around us today. And if you measure the angular power spectrum of that temperature map, so this is essentially measuring, if you like, the 2-point angular correlation function of those temperature fluctuations, and then taking an angular Fourier transform. That's what's shown here, the red points. This is from the Planck satellite, their final results released in 2018. And superimposed on that, the blue curve is the best fit lambda CDM model, again, with these 6 parameters, which is a remarkably good fit to the observations. And so from this kind of fit, we can read off the parameters of the current standard lambda CDM model, again, about 70% dark energy or cosmological constant, 31% of matter, that's both cold dark matter plus baryons. NS is the power spectrum of the initial perturbations, which is close to scale invariant, which would be NS of 1. Hubble constant of about 67, which we'll come back to. Sigma 8 is the current predicted amplitude of fluctuations on 8 H inverse megaparsec scales. We'll come back to that as well. And omega baryon times little h squared is a measure of the current density of baryons in the universe. So it's equivalent to about 5% of the universe in baryons. Okay. So this is, again, just showing the sort of standard pie chart, excuse me, of the cosmic constituents that results from this kind of fit. So again, the CMB is giving us this picture of the very early universe. And then, as I mentioned, we can evolve that picture forward to today using cosmological n-body simulations. So this is just one example of doing that. So initially, the density fluctuations are very small amplitude, but over time, they grow in amplitude due to gravitational instability of both the dark matter and the baryons to eventually form this web of structure, clusters, halos of this case is a dark matter simulation. So in this simulation, we're only forming clumps of dark matter, which we call halos. And then within those clumps are where we believe luminous galaxies and clusters of galaxies form. And again, this we can then, with cosmic surveys that I'll be talking about, we can go out and measure the statistical properties of this structure. And what we observe in our surveys today agrees quite well with the predictions of gravitational instability, starting from those early conditions set out by the cosmic microwave background. So we have this, I think, really remarkably consistent picture of cosmic evolution from early to late times. Oops, sorry. So this is an example of those late time observations. What's shown here, first of all, in the background is simply a map of mainly of stars in the Milky Way. So the Milky Way Disc is shown as this sort of band, this arch going through the middle of around the middle of the image. So that's simply emission from stars and gas in our galaxy. But then superimposed on that is this sort of blotchy, strangely shaped region in the middle. And that's a map of large-scale structure of the mass distribution inferred from weak gravitational lensing observations from the dark energy survey. And by studying the statistical properties of this map and other measurements we can make, we can compare that to the predictions of the CMB, as we'll see, and they agree quite well. So really, as I've said, over the last 25 years, the story of observational cosmology has been one of increasing precision, from really order unity uncertainties to now, in a number of cases, percent level precision on a number of parameters. And as we've made this march of observational precision, the relatively few parameter paradigm has been able to explain all the observations. And I think that in itself is worth remarking on. It didn't have to turn out that way. It could have been that the temperature patterns in the microwave background or the correlations of galaxies and mass that we see in surveys, may have looked at nothing like what a simple model would have predicted. So I think in a way in cosmology, at least so far, we've been quite lucky that a relatively few parameter model has sufficed to explain all the data. Nevertheless, so we have this remarkably successful model, but nevertheless, we really don't understand the basic physics of the key components of this model, which are dark matter, dark energy, and primordial inflation. We haven't yet identified the nature of dark matter. We assume it's a new particle, but it hasn't been observed in the laboratory. We don't yet know the particle physics model of inflation. We have some ideas, but it's hard to constrain. And we don't know the physics of what's driving cosmic acceleration. It could be something we call dark energy, which I'll talk about in a minute, or it could involve something with our understanding of gravity, so-called modified gravity theories. If it is dark energy, the simplest possibility is that it's a cosmological constant, but it could also be some dynamical component, say a new ultralight field in the universe. So we have these basic questions about really 95% of the universe and how those new components fit into our understanding of fundamental physics. So we have this, again, it's sort of an interesting situation in cosmology where we have now really remarkable precision but we're still lacking some basic fundamental understanding of where these numbers come from. So again, I'm going to be focusing on the origin of cosmic acceleration. So just as a reminder, we've known for since the 1920s that the universe is expanding. We have good evidence that it's homogeneous and isotropic around us. And a homogeneous isotropic universe is very simple. It's described by a simple function of time, this so-called cosmic scale factor, A of t, which just describes how physical separations or scales in the universe evolve with cosmic time. And so, ideally in cosmology, we would measure the history of this cosmic scale factor. We can't quite do that, but we'll talk about ways that we try to indirectly get at an understanding of this history of the cosmic scale factor. And of course, we quantified the expansion rate as a function of time through this function h of t, which is just the fractional time rate of change of the scale factor. Okay, so if you assume a homogeneous and isotropic universe described by this simple scale factor, you can then apply the equations of Einstein's general relativity to work out what the dynamics of this scale factor is. And you get a series of equations called the Friedman equations. The one we're going to focus on here is the second order Friedman equation, which relates the fractional second time derivative of the scale factor to the mass energy density components of the universe. So we're focusing on the right-hand side here. G is Newton's constant, and this summation here is over all of the mass energy components of the universe, each one with a subscript I. So rho sub I is the energy density at a given time of the ith component, and W sub I is the ratio of the pressure to the energy density of that ith component, and we call that the equation of state parameter for that component. So for example, for ordinary non-relativistic matter, those particles are moving very slowly. The pressure in dimensionless units is very small compared to the energy density. The equation of state parameter is effectively 0. For relativistic particles, say like photons, the pressure is 1/3 of the energy density, so W is 1/3. And so you can see that if we want to get solutions which are not, so let me back up. If the universe is composed of non-relativistic or relativistic particles, then W is always greater than or equal to 0. Energy densities are positive. And this equation immediately tells you the universe should be decelerating. That is, as the scale factor grows, it should be slowing down in time due to this minus sign on the right-hand side. And that's simply a reflection of the attractive nature of gravity. If we, as we now believe, the universe is accelerating, it's speeding up, the second time derivative of the scale factor is positive, we somehow need to flip the sign of the right-hand side of this equation. And the way to do that is to have some component, I, which dominates the energy density, and whose equation of state parameter W is less than minus 1/3, because you can see that that will then flip the sign of that term and allow the possibility of an accelerated solution. So that is what we call dark. That's the defining nature of dark energy, is that it's some component currently dominating over matter and radiation and other components with an equation of state parameter W less than minus 1/3. A particular example of that component is the cosmological constant, or the energy of the vacuum, which has W precisely equal to -1. So it satisfies this constraint. That's just one example, though, of this more general phenomenon of dark energy. Of course, the other way to get accelerated solutions is to postulate that this equation is wrong, that gravity is not described by Einstein's theory, but described by a modified gravity theory, in which case you can imagine getting accelerated solutions without having an additional dark energy component. And I think Paolo will probably talk about that tomorrow. All right, so in this, we're going to stick with this general relativity assumption. And in that theory, in that model, this is how different components of the universe evolve with time. So the y-axis here is the logarithm of the energy density in different components. The x-axis here is effectively the scale factor of the universe, or the logarithm of the scale factor. So we're here today when that logarithm is 0, the scale factor is unity. And we're, in this case, the universe is dark energy dominated. That's this blue or aqua region here. It's about 70% dark matter, which is this black line, is about 30%. Radiation, which is the red line, is currently only about 1 part in 100,000 compared to the dominant components. But you can see as you go back in cosmic history, in logarithmic terms, you soon reach an epoch where the universe was dominated by matter. So the black curve was on top. And if we go back even further to when the cosmic scale factor was less than 1/1000th of its present size, then the red component starts to dominate. So the earlier history of the universe was radiation dominated. And again, if this aqua region sort of is the band for which W is roughly less than minus a third or so. So again, if W is exactly equal to -1, we get this dark blue curve where the energy density in dark energy is exactly constant with time. It doesn't change as the universe expands. But if W is different from -1, the energy density in dark energy will be slowly decreasing or increasing with time. Okay, so we want to try to understand the nature of dark energy with cosmic observations. How do we do that? Well, we have kind of 2 primary probes at our disposal. One is what we call geometric probes, or probes of the expansion history of the universe. And the other are growth of structure probes. And basically, the idea here is that if we have this component of dark energy added to the other components of matter and radiation, it will have 2 impacts on cosmological observables. One is it will change this cosmic scale factor evolution, and therefore change the evolution of the expansion rate as a function of cosmic time. The other is that it impacts the growth of density perturbations that form structure. So remember, I said that we start with a universe which has small amplitude fluctuations initially. Due to gravitational instability, those perturbations grow in amplitude to eventually form the nonlinear structure we see today. If we have a component of dark energy, which is causing the universe to speed up, then clearly that's going to counteract the attractive nature of the cold dark matter, which is making structure become more nonlinear, more clumpy over time. And so depending on the amount and nature of dark energy, that will change the growth rate of density perturbations over time, particularly at late times when dark energy becomes dominant over ordinary dark matter. And so that's what's shown on the right-hand plot here is the growth rate of linear perturbations in two different models with 2 different values of this equation of state parameter W. So in principle, if we can make observations of the amount of structure as we look back in time, then we'll see that in a universe where W is more negative, we will see less structure as we go back in time relative to a universe in which W is larger than -1, for example. So that's the growth of structure probe. The expansion history probes on the left-hand side are simply due to the fact that when we measure distances to objects, those distances are essentially integrals over the inverse of this cosmic expansion rate. And since the expansion rate is sensitive to, again, the amount of dark energy and its equation of state, then in principle, by measuring distances to different redshifts, we're sensitive to a degenerate combination of the dark energy equation of state, W, and the density of matter in the universe, this omega matter. And again, I should just remind you that redshift here is just a stand-in for cosmic time, but it's really just one inverse of the cosmic scale factor. So as we look back in time, we're looking out in redshift, and we're looking at epochs where the cosmic scale factor was smaller and smaller relative to its size today. So for example, at a redshift of 1, the cosmic scale factor was half of the size that it has today. So you can see that if we can observe distances out to appreciable redshifts of order a half or 1 or more, we can start to distinguish these different cosmological models and therefore get handles on dark energy. You also see that at very low redshifts in the left-hand plot, all the curves become degenerate. And that's just a reflection of the fact that at very low redshift, all we're observing is just the Hubble expansion today. That's the expansion of the universe that was discovered in the 1920s. So our goal with current and future surveys is to try to make these measurements, but now at the percent level of both expansion history and growth of structure to be able to constrain dark energy and other cosmological parameters. So I'm going to go through sort of several of the different probes we have, observations we have to probe both growth of structure and the expansion history. So the first one I'm going to mention is clusters of galaxies. So this is an image of a nearby cluster of galaxies, the Fornax cluster observed with the dark energy survey. A cluster is simply a region of space where there's a number of galaxies within a relatively small space, typically of order a megaparsec or so in size. And so these fuzzy things here are all galaxies within this Fornax cluster of galaxies. If I take this one little region here in red and zoom in on it, again, you see quite a number of galaxies. You see these very bright galaxies, but also fainter ones. And most of the sort of sizable galaxies you see in this image are all within that Fornax cluster. In addition, you see some stars, which are in our own galaxy. Those are the things with these sort of cross-like images. And you see many more faint objects here, which are galaxies that are more distant than the Fornax cluster. So clusters are one of the ways we hope to probe dark energy. Clusters are proxies for massive halos of dark matter. So even though in that image, what we saw was galaxies, we really think that Fornax and other clusters are actually big reservoirs of dark matter within which these luminous galaxies sit. And by using the theory of large-scale structure formation, we can calculate the number of clusters or the number of massive dark halos above a certain mass threshold that we should see as a function of redshift in different cosmological models. So the equation for that is shown in the lower left here. It's showing the number of clusters we expect to see in a certain redshift interval over a certain solid angle omega on the sky. And on the right is a plot of that for several different values of the dark energy equation of state parameter W, holding all the other parameters fixed. And you can see that the curves differ from each other, so that if we can simply go out and measure the number of these massive halos we see in, say, a 4,000 square degree region, which is what this is for, in bins of redshift, then we can simply read off the value of W. And these curves differ from each other in interesting ways. At low redshift, the red curve is lowest and the blue curve is highest. But as you go beyond a redshift of about 0.6, that relationship flips and the red curve is highest, the blue curve is lowest. And that's reflecting the fact that the number of clusters we see is a combination of these two effects we talked about, geometry and growth of structure. At low redshifts, the differences between the models are just dominated by the difference in the volume in those different cosmological models. So that's the geometric effect. That's analogous to measuring distances. At high redshifts, the differences between the curves reflect the differential growth rate of structure in those three different cosmological models, as shown here. And again, as I mentioned before, as W goes up from -1, we expect there to be more structure as we go back in time relative to W of -1, and therefore we'll see more clusters than we would for W of -1. So in principle, all we need to do is go out, measure the number of massive halos as a function of redshift, and we can read off dark energy parameters. Of course, we can't do that. We can't see massive dark halos of galaxies, of matter. What we can see are luminous galaxies clumping together into clusters. So what we do is use clusters as stand-ins for these massive dark halos, and we use the galaxies they contain to infer information about the nature of the dark halos. In particular, we can use the colors of the galaxies to estimate the redshift of these clusters, so-called photometric red chips. And for clusters of galaxies, those estimates are quite accurate, about 0.01 in redshift, or we can simply go out and measure the spectra of those galaxies directly and get a more accurate estimate of their redshifts. The tricky thing is to infer the mass of these clusters, because again, this plot on the right assumes I'm counting everything above a certain mass threshold. We can't directly measure the mass of these clusters, but we can measure things which are good proxies for mass. For example, the number of luminous galaxies that a cluster contains, which is called its richness, is proportional to the mass of the cluster. The more massive clusters will contain more luminous galaxies in them. So that's one way, is to use the richness. There are also other things that clusters do. They scatter photons in the microwave background due to the hot gas that they contain. That's called the Sunyaev-Zel'dovich effect. The more massive clusters will have a larger Sunyaev-Zel'dovich effect, so that's one way to do it. Massive clusters, this hot gas that they contain emits X-ray, so the X-ray flux or temperature is also an indicator of the mass of the cluster. And finally, we can this cluster will bend the light from distant galaxies around it due to gravitational lensing. And so we can use weak gravitational lensing, well, actually weak and strong gravitational lensing, to also infer the masses of the halos associated with these luminous clusters. And that is proportional to the mass as well. So we have a number of proxies that are correlated with the mass of a cluster, each with different degrees of accuracy, different systematic uncertainties, etc. So that's the nature of the cluster probe, and I'll come back to that later. The second technique is weak gravitational lensing. I've already mentioned this. The idea here is that we have distant galaxies. The light from those distant galaxies, as it travels towards us, goes through a bent path as it travels around foreground dark matter halos, for example, clusters of galaxies, or even the halos associated with individual field galaxies, or even just large-scale structure itself. And that bending, those distortions in the path, will lead to an apparent distortion in the shapes of these galaxies. So galaxy around a perfectly circular galaxy will appear elliptical due to this weak gravitational lensing effect. It's a very small effect for typical galaxies. The shape is only distorted by about 1% or so. But we use the fact, and galaxy shapes, are vary much more widely than that. Galaxies are not intrinsically circular. So by looking at an individual galaxy, I can't tell how much it's been lensed, but we can use the fact that galaxies nearby each other on the sky, their light paths go through similar foreground distributions of dark matter, and therefore get bent by a similar amount. So these distortions are highly correlated over small angular scales. And by measuring the shapes of a large number of galaxies per unit area on the sky, we can essentially tease out the gravitational lensing effect from the noise due to the different shapes of galaxies. And again, those distortions, this weak gravitational lensing effect, depends on both the distances to these galaxies, so that's the geometric probe, as well as the expansion history, which determines the growth of these dark matter halos that are doing the lensing on the way to us. So again, like clusters, weak lensing is sensitive both to geometric and growth of structure effects of dark energy. So here's just an example prediction. This is the angular power spectrum of the weak lensing amplitude as a function of angular multipole L for source galaxies in 3 different redshift bins. So Z4 is galaxies correlated with galaxies in a 4th redshift bin, so a very distant redshift bin. Z2, the lower curve, is correlating the shears of galaxies in a nearby redshift bin, so the amplitude of weak lensing is lower. And then the middle curves, Z2, Z4, is cross-correlating the shear of the more distant galaxies with the more nearby galaxies, and that will be intermediate in amplitude between the two. And then the red and the blue curves are for 2 different values of this dark energy equation of state, and the black points are a prediction for W of -1. So again, in principle, if we can measure this lensing amplitude as a function of angular scale and redshift, we can try to tease out the impact of, say, dark energy equation of state on this observable. And we'll come back to that. Third probe is Baryon acoustic oscillations. So this comes about by measuring just the actual spatial clustering of galaxies, either in 3-dimensional space with a redshift survey, or I'm going to be talking about it in angular space for galaxies in photometric redshift. So this is galaxies binned in redshift by their colors, essentially. Those galaxies, due to large-scale structure, are correlated with each other. And because of the physics of the baryons and the photons prior to recombination, there's an oscillatory feature in this angular power spectrum of galaxies, which is essentially reflecting the same oscillations we saw in that CMB temperature angular power spectrum at the beginning of the talk. So the same physics which imprints on the microwave background as a sort of ringing in the angular power spectrum also imprints to much smaller degree, much more subtly, as a ringing in the angular clustering of galaxies. So again, here's a prediction for angular power spectrum of galaxies in 4 different redshift bins for several different values of this equation of state parameter W. So this tells you that if we could measure the angular clustering of galaxies in different redshift bins, that in principle we could tease out, by looking at the angular multipoles where we see peaks and troughs, we could tease out the effects of the dark energy equation of state. So that's the third technique. The final technique I'm going to talk about is type 1a supernovae. This was the technique that was originally used in the late 1990s to discover really sort of give us direct evidence that the universe was accelerating. And this is, again, a purely, like the BAO, this is really a purely geometric effect, just probing directly the expansion history of galaxies. And so on the lower left, I'm plotting a logarithmic measure of distance, mu, versus redshift. So this is sort of data now analogous to that left-hand plot I showed for the cosmic expansion history growth probe before. And so by comparing those different model curves, as I varied W and omega matter to these data points, I can constrain a combination of W and omega matter as we saw before. And I'll show an example of that later. Okay, so we have these four techniques, these four observational probes. These are not exhaustive. There are other probes of dark energy, but these are the ones I'm going to focus on for today. And I'm going to use the dark energy survey as an example of how we make these measurements and what we've learned so far about dark energy from them. So the dark energy survey was designed in the early 2000s to carry out a large area survey over about 5,000 square degrees in the southern hemisphere, and took data from 2013 to 2019. To do this, we built a new wide area mosaic CCD camera called the Dark Energy Camera that was mounted on the prime focus of this 4-meter telescope at Cerro Tololo Inter-American Observatory that I showed you before. And over the course of 6 years, we observed hundreds of millions of galaxies and also carried out a time domain survey over a more limited part of the sky to discover a few thousand of these supernovae. The whole survey took about 575 nights, and you can read more about it at this darkenergysurvey.org. To put together a project like this, you need a large collaboration. We have hundreds of scientists from 26 institutions in 7 countries. This is a picture of what the dark energy camera focal plane looks like while it was in the laboratory before it was mounted on the telescope. Each of these little rectangles you see is a CCD detector with about 2,000 by 4,000 pixels in it. And these are very sensitive detectors. They can detect very low levels of light coming from the night sky. The area covered by this camera on the telescope is about 3 square degrees. So it's quite large by compared to most astronomical instruments in use today. This shows you sort of what the scale of that, the physical scale of that focal plane is. These are 2 technicians handling one of the filters that covers that CCD focal plane. We used 5 of these filters. So in each observation, we would carry out, we would detect photons in a particular wave band of the optical spectrum, going from the blue end with the G filter through RIZ-Y into the near infrared range of wavelengths. So in each image from DCAM, you use one of these 5 filters. And by measuring each part of the sky sequentially through these different filters, we then get color information and therefore photometric redshift information about all of the galaxies in the survey. And a feature of this particular camera is that these CCDs are very thick compared to conventional CCDs. So their quantum efficiency, particularly in the I, Z, and Y bands, is very good compared to conventional thin CCDs. And that's important because we were trying to probe galaxies out to redshifts of order unity, and having that additional efficiency in the red bands was very important for that. So here's just another image of the camera in the upper right, mounted on the top end of this telescope. The primary mirror, which is 4 meters across, is shown in the lower left of the picture. You can see it reflecting light. And this blue structure is just the housing, the mount of this telescope, which allows it to point in different areas of the sky. And then surrounding the whole thing, you see that dome, which on the outside is that silver color we saw in that earlier picture, and which we show again here. Okay, so this is what a non-typical image from the dark energy survey looks like. This is a particularly beautiful nearby galaxy, but we're really interested in these very small smudges of galaxies, which are much more numerous and much fainter, and measuring their properties, their colors, their shapes, than in these very bright nearby galaxies. So all this data has become, I'll be talking about results, but all this data is in fact, most of the data from the survey is now public. We've released earlier last year all of the basic data from the survey, from the 6 years of the survey. We actually just released yesterday some additional catalogs from the survey. And so anyone can go and download this data, analyze it, carry out whatever sort of analysis you might be interested in. I think this is a real achievement in the quality of this data. The photometric calibration precision of this data is much better than 1%. And that's much better than we told ourselves we had to do and much better than we expected to do. So this data really is of exquisite quality. The typical images have a point spread function of about 0.9 arc seconds. That's about as good as we expected to do. It's a little bit better in the red bands. And the depth of the survey is about 24th, a bit more than 24th magnitude, which is what enabled us to measure, have high signal to noise measurements of these hundreds of millions of galaxies over this 5,000 square degree region. So I now want to turn to the sort of the heart of the analysis we've done, and the analysis that we released in May of last year, called the 3x2 point analysis of the first 3 years of data. We're still now analyzing the total 6 years of data for cosmology, but last year we released analyses of the first 3 years of data. Whoops, excuse me. So basically, 3x2 means we're measuring 3 different 2-point correlation function measurements. So the first one is galaxy clustering. We're measuring the angular correlations of about 11 million what we call foreground galaxies. So these are galaxies at modest, somewhat modest redshift. We're then measuring the shapes, the correlated shapes of 100 million more distant source galaxies. That's called cosmic shear. That's what I showed you the predictions for that before. And then we also measure the cross correlation between the shapes of these source galaxies and the angular positions of the foreground galaxies. That's called galaxy-galaxy lensing, and it measures the galaxy mass cross correlation. So that we're essentially measuring the tangential shear of the source 100 million source galaxies around the positions of these 11 million foreground galaxies. This turns out to be a quite complex measurement involving, as I mentioned, scores of people. The whole thing is described in 30 papers that were released last May. Involves quite a number of developments of analysis methodology that I don't have time to talk about, but I invite you to peruse those papers from the DES collaboration, because a good part of what we've done with DES is not only have this data, but really have pushed forward the methods to analyze these data, which will be used in future surveys as well. Here's a snapshot of many of the people who were involved in this analysis. As I mentioned, it's a complicated pipeline of analysis that I'm not going to go through in detail. I just want to hit some of the highlights since we're getting short on time. So one thing I mentioned is that a backbone of all these measurements is this thing called photometric red chips. So the idea is for each galaxy, we have its flux or its magnitude in these 5 different filters, G, R, I, Z, and Y. For cosmology, we basically use the G, R, I, and Z filters. And we know that by measuring the color of a galaxy, that's in these different filters, that is the relative magnitudes or magnitude differences in these different filters, that gives us a pretty good estimate of what the redshift of the galaxy is. It doesn't give us an exact estimate, it gives us a probability distribution. And the basic idea is that as I redshift a galaxy, shown in the right here, this is the spectrum of an elliptical early type galaxy. It has a pronounced feature at 4,000 angstroms in the rest frame. As I move that galaxy out in redshift, that feature moves out in observer wavelength. And therefore you can see that the nearby galaxy has quite a bit of flux in the G band, say relative to the other filters. But for the redshift 1 galaxy, it has no flux left in the G band. So it's going to have a much redder color. So by using these, by training this relation with, say, neural networks or other machine learning algorithms, we can get quite good probabilistic estimates for these photometric redshifts based on the multiband fluxes from these galaxies. So that's shown here. We had actually 2 different foreground samples, one called Red Magic, which is red galaxies. The other is this Maglim sample, which is the one that we're using for this analysis. And then so these are both these samples of 10 or 11 million galaxies. The sample of more distant 100 million sources is the weak lensing sources at the bottom. Those photometric redshift estimates you can see are not as precise. These are fainter galaxies where we just don't have as good mechanism to estimate the photometric and to train the photometric redshift estimator. Okay, so with all of that, you have your sample of 100 million galaxies with photometric redshifts. You measure their positions on the sky, their photometric redshifts, and for the source galaxies, you measure their shapes, use that to estimate the cosmic shear. And then we form these 3 different 2-point correlation functions. So let's start with the lower right one. That's the simplest one, galaxy clustering. So red means it's a foreground galaxy, and I'm simply correlating the positions of one foreground galaxy with another one. So that's this thing between those 2 red points. And I'm showing you the angular correlation function of galaxies in these 4 different redshift bins. 1,1 is the nearest redshift bin, 4,4 is the more distant one. And plotted on top of that, the curve is the best fit lambda CDM model, which you can see fits pretty well. In the left-hand portion, I'm showing you the same thing, but now for cosmic shear, where we're correlating the shapes of galaxies, of these 100 million distant source galaxies with each other. And now we correlate them not only with source galaxies in the same redshift bin, but with source galaxies in other redshift bins as well. So in the left-hand side, for example, the 1,1 in the lower left is showing you the shear correlation for source galaxies in the nearest redshift bin. The 4,4 in the upper right is showing you the shear correlations for the most distant galaxies. And then we're showing you all the cross correlations as well. Again, the solid curves are showing you the best fit lambda CDM model. And finally, in the upper right, we're showing you the galaxy-galaxy lensing, the cross correlation between the shapes of the source galaxies and the positions of the red foreground galaxies. Again, for different redshift combinations, again, showing you the best fit lambda CDM model. I should say, when we fit these, the cosmological models to this, we don't simply have the 6 cosmological parameters to worry about. We also have, in fact, 26 so-called nuisance parameters, which describe, for example, the uncertainties in the photometric redshifts, or calibration errors in the shear measurements. So those all have to be, because we have uncertainties in those, we include them as nuisance parameters, which we then marginalize over to derive cosmological constraints like we're showing here. So this is an example of results from cosmic shear. So this is the thing that was in the left-hand plots in the previous slide in blue. And then in the orange here, we're showing you the combination of constraints from the galaxy clustering and the galaxy-galaxy lensing. The parameter space I'm showing here is matter density, omega matter, on the x-axis, and the clustering amplitude that we call S8, which is a combination of the actual density perturbation amplitude, sigma 8, and the square root of the matter density. The reason we plot S8 is because that's the thing that the cosmic shear sort of measures reasonably well. And so this blue contour is sort of relatively flat in this plane. And you can see that the results from the cosmic shear and from the two other two-point functions are consistent with each other. So we can combine them to make the results from these three two-point correlations. That's shown in the gray region here. And we can read off estimates for S8, omega matter, and sigma 8. Okay, that's good. How does this compare with things like the cosmic microwave background? Well, it compares pretty well. So here we're showing the same plot on the right, but the green is now the inference from the Planck cosmic microwave background measurements, again assuming lambda CDM. And you see that these two contours overlap quite well. They're certainly statistically consistent with each other. And that's interesting because prior to these measurements, if you look on the left, there has been some hints that the CMB measurements, which are shown in the gray region on the left, were a bit above the constraints from lensing measurements from the cosmic surveys, which are the other colored regions here. On the left, I'm not showing S8, I'm showing sigma 8, but it gives you the same impression that there was some hint of a tension between the weak lensing measurements being a bit low compared to the CMB measurements. But we're not seeing that in any statistically significant way with these latest results from the dark energy survey. They're perfectly consistent with each other. Since they're consistent, that means we can combine the DES and the Planck measurements and get this orange region here and get a kind of a best estimate of these cosmological parameters. But you can also compare these to other sorts of measurements. So that's shown in the orange curve here, is using other low redshift measurements from spectroscopic survey, BOSS and eBOSS, and also from supernovae from the Pantheon compilation. That's shown in the orange here. And if I combine, and again, green here is Planck, gray is DES, purple is now the combination of DES with the other low Z measurements. And again, they're all now appear to be consistent with each other. That was all assuming lambda CDM. If I now broaden out the model and say, okay, I want to know about W, everything I showed you so far assumed that W was pinned to -1. We're now going to let W be a free parameter and do the same analysis. And that the analogous plot is now shown on the left here. You can see that that changes the shapes of the contours, particular for the CMB. The CMB does not constrain W particularly well. So W is marginalized over here on the left. But we still have consistency between these different probes. We can also directly constrain W. That's shown on the right. Again, gray is DES, green is from Planck, orange is from these other spectroscopic and supernova surveys. Purple is putting together those surveys with DES, and blue is putting everything together. And you see it's perfectly consistent with W of -1 with an error of about 0.03. Again, assuming W doesn't evolve with cosmic time. I think I don't have time to talk about baryon acoustic oscillation measurements from DES. If people have questions about that, I'm happy to discuss that. I want to say just a couple of words about another cosmological parameter, H naught, the current expansion rate of the universe. This is a parameter where there has been now claims of a significant tension between measurements from Planck CMB, shown here in gray, and local measurements from supernovae and Cepheid variables, shown in blue. And the recent results from the Shoes collaboration now puts this as at a 5 sigma discrepancy. There is another local measurement using tip of the red giant branch, shown in red here, which fits in between these two. What does DS, what do these cosmic surveys say about this? Well, the observations of these 3 2-point functions don't constrain H naught directly, but they help break degeneracies in determining H naught in combination with other data sets. So here's an example of that, showing omega matter on the y-axis, the Hubble parameter H on the x-axis. The purple is an older version of the Shoes result. That's now even smaller error bars centered on 70.73. And now the gray region is if we combine these 3 2-point measurements from DS with baryon acoustic oscillation and Big Bang nucleosynthesis estimates shown here. The Planck results are shown in green. If you combine that all together, you get this blue contours, again, centered on about 0.68, and again, showing that there seems to be this discrepancy. And the interesting thing is that the black region here is not including the Planck CMB measurements. So we can even remove the CMB, and we still have a tension between these large-scale structure measurements and the Shoes local measurements of H naught. I don't have time to talk about strong lensing or gravitational waves, but or clusters, unfortunately. So I'm going to skip to actually, I want to say a few words about supernovae. So as I mentioned, supernovae were the original way we discovered that the expansion is speeding up. Here is a 4-band light curve for one of the several thousand type 1a supernovae discovered with DES. So here we observe the same patch of the sky repeatedly over the course of a couple of months, and we see a supernova get brighter and fade in these different pass bands. We can go up and measure the redshift of the supernova with other telescopes, and the shape of this light curve tells us that it's definitely a type 1a supernova. Here's an example of what it looks like for a much higher redshift supernova at a redshift of 1. All the light has shifted out of the blue band here, and it's mostly in the redder bands. So this is our first year result just from the first 3 years of data, distance versus redshift, for only a few hundred of these spectroscopically confirmed supernova from DES. Again, if we combine that with measurements from BAO and CMB, again, we get constraints consistent with omega matter of 0.3, W of -1. Soon we will have results from a much larger supernova sample and expect to get correspondingly tighter constraints. That analysis is still going on. Unfortunately, I've run out of time to talk about other interesting results from DES. I just want to finish by mentioning, excuse me, that we have a number of other cosmic surveys that have either started or are soon to start. Excuse me, I'm just going to get some water. I'll be back in 10 seconds. Sorry about that. So in the upper left is DESI. This is a big spectroscopic survey using the Kip Peak 4-meter telescope in Arizona. and it's already accumulated more redshifts than all previous redshift surveys combined, quite impressive. On the upper right is the Vera Rubin Observatory. This is a 6.8 meter telescope being built near Cerro Tololo that will carry out a 10-year massive multiband imaging survey, much deeper and over a much larger portion of the sky than DES. And the lower panels are showing you renderings of the Euclid and Nancy Grace Roman space telescopes, which will be doing similar measurements from space. So we're really now just about to enter, or just entering, this golden age of much more ambitious cosmic surveys, which will accumulate much more data than we've had from these previous and current generation of surveys. So we're in this interesting transition regime. I think it's important because we don't yet know, even though W is consistent currently with -1, as shown here, the error bars are still significant, and we don't know whether dark energy is in fact the cosmological constant or might be something different from it. And I think we're really going to need this next generation of surveys to answer this question more precisely. I should say that, you know, collectively, these future surveys are costing the world several $1 billion. That's quite a lot of money. And I think, though, there's a lot of work to be done to make sure that we further develop the tools to extract all the information from these surveys. So one thing I didn't tell you about, but was kind of embarrassing, is that when I showed you these data and these beautiful fits from Lambda CDM, I didn't tell you that these gray regions are regions of data that we didn't use in the analysis because we don't yet trust the accuracy of our theoretical models on those scales. This, to me, is something of a scandal. You can see we're effectively throwing out half of our data simply because, not because it's not measured, it's measured extremely well, but because we don't yet trust the tools we have to extract the information from those data points. And clearly we need to do this. This is going to be even a bigger problem for these coming surveys. And so we need lots of people perfecting these methods to really do much better than we've done so far. Okay, so I'll stop there and happy to take questions. And I apologize for going over.
Thank you, Josh, for that excellent lecture. So I will see if there are any questions, if people want to raise their hand. So we have Pong. Go ahead.
Hi, Professor. Thank you for your lecture. So I have like two questions. The first one, beside the SA tension and the Hubble tension, what any tension do we have from the data?
For which? Sorry.
So what other tension do we have?
Oh, what other tensions? Is that what the question is?
Yes.
So far, I think S8, and again, I don't think S8 is much of a tension anymore, based on this. Although we'll see with these future surveys. I think I think H naught, there is clearly a tension between the Cepheids and the CMB. It could be something going on with the Cepheids, since the TRGB seems to be a bit lower. And also, the point is it's unlikely to be a systematic associated with the CMB for this reason here, that we can even, we don't just depend on the CMB for this tension. There are other methods that we're using to try to measure H naught, strong lensing time delays, in the future gravitational wave standard sirens. So I think eventually we'll have a multiplicity of ways of measuring H naught that will come to help us resolve this tension. In terms of other tensions, I don't think we have, so far as I know, really significant ones. The other parameters, we seem to have good agreement between, say, the baryon density is fully consistent between Big Bang nucleosynthesis and the cosmic microwave background. I think the other parameters, we either don't have tensions or we don't yet have multiple different methods of precisely measuring the same parameter. So I think it's, so far the picture is holding up quite well. Again, I think it'll be interesting with these stage 4 experiments. They're going to have, in principle, greater precision if they can extract all that information. And so I think it's very likely that in the future, we will see more tensions, because when you measure a whole bunch of parameters with high precision using different methods, you're going to see tensions. Whether they're real or not will wait to be seen. But I think this sort of era of tensions is probably only just starting, which makes it fun.
Okay. Thank you. And for my second question, like for a theorist, for your view, if we trust the experimental result, if we trust the data and we see a tension there, so what kind of mechanism, what kind of theory we can come to think about to show the Hubble tension, you know,
Okay.
like to modify the potential or something like that?
Right. Yeah, that's a good question. So I think there's been a lot of literature in the last 3 years on the Hubble tension. So let's assume, right, so you're saying let's assume that the shoes measurement is correct, say, and that the CMB measurement is correct, so that there really is some kind of tension between the lambda CDM based inferred value and the local value. Mm-hmm. If that's the case, then I think a number of papers have shown that the best hope for trying to resolve that is to change the lambda CDM model, but you have to do it in a very particular way. It seems like the best hope is to modify the expansion history of the universe just before recombination. So, you know, a couple 100,000 years after the Big Bang. For example, by introducing a new component. So there's a whole bunch of so-called early dark energy models where you arrange for there to be not really a cosmic acceleration, but basically I'd say 5 or 10% admixture of dark, quote unquote, dark energy, which becomes a relevant contributor to the expansion rate just before the epoch of last scattering or recombination. And there have been some studies showing that if you do that, then that essentially doesn't change the pattern of the CMB fluctuations, but it changes your interpretation of that pattern in such a way that it enables, it's consistent with a larger value of H0 instead of 67, you know, maybe 70, something closer to the shoes value. So again, that's, you know, whether those models are really consistent with all the data is I think controversial. They're certainly quite contrived, right? You basically have to say that there's some third dark energy component in addition to inflation and what's going on now. And you also have to arrange that it doesn't dominate, it just contributes 10% of the total energy density over a narrow range of expansion. And then it has to disappear very rapidly in a way that you don't expect in sort of the simplest models you would write down, so that it doesn't impact other observables. So these models are quite contrived, but it shows you sort of the kinds of, you basically have to stand on your head, I think, to come up with models that really reconcile this. I think that's a real tribute to the precision and accuracy of these data, that it's becoming we're having to do things that appear quite Baroque from a theoretical perspective to make these things consistent with each other. Perhaps a theorist will come along, with an idea that's much simpler that does that, and I think that would be great. But at the moment, the models I've seen for this, they're not something you would have naturally thought of without being pushed into it.
Thank you, Professor. My girlfriend is a big fan of your she study cosmology.
Oh, great.
Okay, so the next question we have is from chat. Muhammad Ali Shabazz wants to know which programs or softwares are in use for these calculations. If someone wants to join these programs, what should we learn?
Oh, I see. To carry out these kinds of data analysis. Good question. So there's really a variety of software packages that have been developed for these kinds of analyses. And as I mentioned, each one of these, making each of these measurements these days involves sort of teams of people developing and then refining these methodologies. That's a good question. Is there some way? Let me look into that. I think much of these packages are in the process of being made public, and so my suggestion would be, look at some of these DS papers. Again, if you just look at, say, DS collaboration in May of last year on the archive, and then that'll have references to these other 29 papers. And then those papers will go into details about the methods. And they will also tell you, okay, we used this software package to do this. And if it's publicly available, this is where you get it, from GitHub or something. And so I would say, though, it's a good question, because I think, there tend not to be sort of unified packages where you can start ab initio, download this data, put it into that, and have it output, plots like this or like this. I think they should exist, but they're not yet, for the most cases, I think, quite that user friendly. There are individual packages that do these things. So, for example, there's a package called Cosmosis, COSMOSIS, which is a package where you can input measurements like this and then have it output constraints like this. But you have to give it a bunch of other assumptions and parameters as well, because again, here I'm just showing you the measurement. To actually make these inferences from those measurements, you also have to have a model for the covariances between all of these measurements. Those are quite complicated in themselves, and there are packages that will theoretically calculate those covariances for you, like Cosmosis. Cosmo-like is another one. But so my suggestion would be really go to the DS collaboration paper from May of 2021 with the DS year 3 3x2 point results, and then use that to trace back through some of these 29 papers, and they will tell you which of these packages they used. And some of those are public, or at least versions of them are public. But I think what I take from your question is that I think as a community, we need to do a better job in developing and sort of homogenizing these tools. I think actually the LSST Dark Energy Science Collaboration is doing a good job of developing these tools in a more sort of community user-friendly way. So that would be my suggestion also, would be, if you're interested in this kind of thing, to connect with the LSST DESC, Dark Energy Science Collaboration, and explore. They have different working groups that people can join, and they are trying to sort of take these tools forward to the next generation.
Okay, thank you. So we have one last question. So has DES carried out analyses with dynamical dark energy models, say related to the Hubble tension?
Sorry, with what dark energy models?
Has DES carried out analyses with dynamical dark energy models, say related to the Hubble tension?
Okay, yes. So we did for the year one results, we did carry out an analysis for what we call extended models, which go beyond just lambda CDM or constant W models. And we're now doing that same thing for the year three result data, the data I'm showing you here, and we will do that for the year six, the final analyses as well. I don't know that we've specifically looked at, say, early dark energy models in those analyses, but we've certainly looked at, say, models with evolving equation of state parameter. So we don't yet have the year three results out, I believe, for that, but those should be coming soon.
All right. So if there are no more questions, and thank you very much, Josh, for that really excellent talk, and I'm sure the students really learned a lot. So to everybody else, again, thank you everybody for participating, and we will see you tomorrow for continuing lectures on we have gravitational waves and some more dark energy stuff tomorrow. All right.
Great.
Thank you. Thank you again, Josh.